but really we're here to listen to Professor Abel talk to us today about his research projects. But we at DesignSafe on our portal, we believe that we can provide a lot of service really from the beginning of your research project to the end. And I'll just kind of leave it at that and not go into a lot of detail, but there's a lot of data sets available. There's a lot of tools that link to or are backed by our supercomputing resources at the Texas Advanced Computing Center at UT Austin, University of Texas at Austin. And we do offer curation and publication services through the portal as well. You get a DOI for your published data sets, published projects. So we'll just kind of leave it at that. Who can use DesignSafe, I think, is another great thing that people want to know. Most anyone in the world can get an account and use these resources. And you can do some data analysis. You can use some of the tools we provide through the portal. And also practitioners. Now we are nominally open science research, but we have a lot of published data sets that are really interesting for practitioners. There is no cost. There's no price to use these services. That doesn't cost any funding because the National Science Foundation in the United States already pays for everything that we need to provide you these services. If you are a practitioner, if you are in industry and you want to use high performance computing, you can reach out to us at TAC, and we do have a way for you to access purchase time. But for any open science, open academic research, you can use our systems. And this is going to be a monthly webinar series with STKO. We've worked closely with Guido Kamada and Massimo Petracca over the years, and so and ASDEA. And so we are very happy to work with them and have this webinar series. You'll see a roughly monthly starting not in December, but we'll pick back up in January and with these webinars. And here's some upcoming topics listed here. So it covers a wide range of activity. And I'm going to turn it over right now to Professor Abel, and definitely does a lot of work in high performance computing, computational research. And so looking forward to hearing what Jose has to say today.
Hello, I just shared my screen. Is it visible?
Yeah, it looks great.
Great. So I wanted to move this bar around. Okay, there we go. So thank you, Tim, for the introduction. Thank you for the space. I want to thank DesignSafe in first place for giving me this opportunity. And also the very good people at ASDEA Software, Guido Kamada, Massimo Petracca, for helping out with this and bringing to your guys' attentions the stuff that I do over here. And of course, my institution of origin, Universidad de los Andes in Chile, where I am sitting in this moment. So today's talk, I'm going to tell you about domain reduction method and a little framework I've set up with the people at ASDEA and my research collaborators here in Chile, which involves ShakerMaker, a new open source Python library for generating seismic datasets, STKO, which you guys know well, and of course OpenSees. So we're going to be going through this this outline. I'm going to be talking to you about giving you an overview of SSI modeling, soil structure interaction modeling, and then a brief introduction to direct domain reduction method, to the theory behind it. Then I'm going to introduce ShakerMaker and how you can use this to generate earthquake datasets. Some aspects of finite element model setup for use with DRM. And finally, I'm going to show some ongoing research results that are part of my current research project here, funded by ANID down here in Chile. So first of all, let's locate ourselves geographically. I'm in Chile right now. So I like always to do a little zoom when I'm doing talks over Zoom. So there's Santiago, kind of in the middle of Chile. And towards your right, you have the Andes mountain range. And if we zoom into, we're doing a little 3D view here, into where I am working right now. Universidad de los Andes is this campus by the foothills of the Andes towards the east of Santiago. And we have a very beautiful campus that we'd like you guys to visit whenever you get a chance. It's a small university, small private school over here, and we're doing stuff, different things with very high results, very good results. Anyway, so one of the problems in Santiago, if we zoom back out into the overview, engineering problems that we have is that we have this fault over here called San Ramón fault. And this fault is the last earthquake occurred maybe tens of thousands of 8,000 years ago, and the previous one 17,000 years ago. So we have basically this reverse fault going under the Andes and right by the edge of Santiago, which we know it's a 30-kilometer long fault, and we know can produce earthquakes, and we have no records for those earthquakes. So one of the things in my research right now is, well, not answer this question, will an earthquake occur? We'll leave that to the seismologists and specialists. But if an earthquake occurs, what kind of motions can be expected? Surface waves, will they have a predominant role in structural response? And are structures designed with current codes, are they safe, or what kind of performance can we expect out of them? And then near field effects, because when you have such a shallow fault, as you guys know over there at the US, you get near field effects and very large intensities very near the fault. This is a type of earthquake that Chilenos would not be used to over here. It would be a very different thing. And my research is going to focus on tall buildings, on buildings, buildings in general. And we have reason to believe that nearby fault might enhance accidental torsion due to wave passage effects. We want to look out for that. But we have no ground motions. So what can we do? We don't have GMPs. We can refer to similar areas. What we need to do is simulation. And simulation of the wave propagation problem. This is what we need to respond to this. And you guys over there at DesignSafe have some data sets. I'd be very happy to talk about those data sets and sharing my own data sets into DesignSafe and seeing if people that are doing high performance, high fidelity seismic simulations, if they'd like to adopt the data format that I'm proposing to do DRM. I'll talk about this in a little while. So these are typical questions you might get at a conference. Did you consider soil structure interaction? Did you include soil structure interaction effects? And this is not an approach I particularly like. I like to think about building systems and whether including explicit soil domain modeling is pertinent to whatever performance metrics you happen to care about. Okay, so the conceptual model is you have some source fault at some depth, and you have propagation from that fault as body waves into the structure, and then you also have interaction with the free surface that produces surface waves, and those come in. The whole point here is that the wave field is three-dimensional and very complex. So you can start at a level 0 modeling. I'm going to go through this pretty fast, where you fix the base and your earthquake input occurs as a series of inertial forces. And you can also start to consider flexibility of the soil by adding springs, and you can make those springs non-linear, and you're increasing your model fidelity, allegedly, if you're doing it right. Or you can go to a level 2 where you're modeling your soil as a continuum. And this is meant to model the near structure soil volume. So you're still modeling the earthquake input as a series of inertial forces, but you want to include some of the maybe local plasticity or settlements, and you want to include interaction between different foundations. And you can also go to the next level. Level 3 is to actually consider the propagation into the site. And in this case, you leave behind the non-inertial reference frame and you go into a inertial frame of reference, and your earthquake is input as a series of tractions at the bottom boundary. And in order to do that, you need to approximate the seismic wave field as a plane wave. So it's a flat wave approximation that you need to do in some sense. So what's a level beyond this? Let me tell you what the problem is beforehand. And here I stole a little video from SKEC that shows what the problem might look like. Like when you have an earthquake propagating, especially in this case, which is a strike slip fault, the motion is not coming from the bottom. It's coming from the sides as surface waves, and maybe with an inclination from below. It's coming from everywhere, so it's a complex thing. So we know deep down in our hearts that this flat wave assumption is not adequate. It's not at least physically realistic. So how do we deal with the spatial complexity of the input wave field? And the answer to that is the domain reduction method. The domain reduction method is a method proposed in 2003 by Jacobo Bielak and Yoshimura and some other authors, right? And I'm going to give you a little bit of an introduction. This is a very beautiful method. It's a very simple method. These are beautiful equations, the kind that you can really grasp in little time. So the basic idea is to separate the problem into two scales, we might call. So it's a regional scale and maybe a local scale, which has a feature. And then you set up the discretized field equations for this problem. And after some algebraic manipulations, you can replace. Look at what happened between these two slides. You have the feature in the full problem. And you remove the feature to kind of like a featureless or free field condition, right? And you analyze in that case the regional problem. And if you do some algebraic manipulations, which I developed for a recent webinar for SDA, but I kind of summarized here, you can actually replace the problem by some effective forces, which vanish everywhere except in a small region around feature, which is one finite element thickness in size. And you have to keep track of what the internal boundary is and the external boundary is. So the earthquake is input as a series of forces there. And so using DRM occurs in two steps. One, you have to solve for the crustal propagation problem in the free field or a regional scale problem. And then you have a local scale perturbed problem where you input the free field regional scale motions into the local scale problem, assuming there's little interaction between the two, or there's not much influence of the feature with respect to the motions. We can discuss what the size of the DRM size need to be, the DRM box needs to be. But that's the assumption. It's a rather good assumption. It rather works nicely. So your finite element models at level 4 end up looking like this. You have the feature, which in this case is a building, but can be some nonlinear soil or whatever you want, a dam, whatever you want to be analyzing. You have an internal domain. You have equivalent nodal DRM forces, which occur which kind of look like this, the forces that tend to kind of balance out. I'll show you what that looks like in a while. And then you have an exterior boundary that you can use to absorb outgoing seismic radiation or outgoing motions, which are actually mismatches from the motions that are produced by the perturbation inside the domain. And the interface between the two domains, the interior domain and the exterior domain, is where input occurs, and we call that the DRM element layer. So regional model, local model, you compute the effective boundary and external forces with these very, very simple finite element equations, which just involve the mass matrix and the stiffness matrix for the one single element layer here. And you need to know, and this is the big problem with DRM, is that you need to know accelerations and displacements for all nodes located at that boundary. So that means these data sets need to be huge if you have a lot of elements. And you can only get that kind of data from simulations. So even if you have some data, you're not going to have a data with the sufficient spatial resolution to get that. At least not in our budget down here in South America. So pros and cons of DRM. DRM can do realistic 3D input. This is a nice one that I like. There's a separation of where earthquake input occurs with where you need to apply static boundary conditions and where you can do damping. So earthquake input occurs inside the domain, and then outside the domain, you can use that to model radiation damping, apply static boundary conditions. So you don't need one boundary to do two things at the same time, as in other modeling approaches. You separate, and this is a good thing about DRM. And then that gives you several options for how you want to model what goes on outside the domain. So that radiation damping, I'm going to talk about absorbent and stereo domain, but you can do Leismer-Kuhlemeyer, you can do PML. And you can also use DRM for traditional 1D analysis, and that gives you the advantage of inheriting all the pros up there, but you can use a seismic record, do deconvolution, assume that you have a plane wave, and input that as if it was a DRM analysis. Now, there is no overhead with respect to other analysis types. DRM input is just some forces. Now, the cons, you need big data sets, easily over 1 gigabyte, 5 gigabytes is rather typical. DRM datasets need to be simulated, although Boris Jeremic over at UC Davis is doing some work on the convolutions of records into DRM. So that's exciting stuff. And it's not yet widely supported and known. So this is something I want to fix. Like I want more people to adopt DRM for their day-to-day engineering, or whenever it's needed. When it's needed is a question that we have to answer. So out of all these levels, here I have like all the levels, simulation levels you can pick, and in big over here is the level 4 with the DRM. How do I know which level to choose for a particular structure that I'm interested in? What level is right? In other words, did you include SSI effects and how? Well, that's going to depend on context. And context means what type of motions are going into your domain, what is your near field geology, but also what metrics or what performance metrics you're interested in. Are you interested in floor spectra or drifts or base shear? So in all these things, I think the general consensus in SSI and soil structure interaction research is that you have to see to believe. You have to really model incrementally until you're satisfied with your modeling. And so if you're going to model fixed space, you have to kind of show that fixed space is enough, at least if your structure is of any importance. So my research is kind of focused on just giving insight into what level is appropriate for this particular scenario. Now, DRM, where do I get motions for analysis with DRM? So I'm very glad you guys asked this question because I've developed a little tool called ShakerMaker. Now, if you look for on Google, you'll find it's also a song by the British band Oasis, which is on purpose. That's where I took the name from. But I like the name, so I just went with it. So ShakerMaker was developed with my colleague and brother-in-law Jorge Grempin at Pontificia Universidad Católica de Chile, and my colleague over here at Wandes, Matias Recabarren, who is Jorge Grempin is a engineering seismologist, and Matias, he's a computer science doing research in software engineering and other things. And we came together with our little team and we developed this little tool called ShakerMaker. So the idea is a tool that facilitates the simulation and also the storage of DRM data sets. So it's both a tool and also I'm proposing a data format for storing the DRM. We need a format to exchange this type of files, and every team has their own. I'm just proposing something that might be of general use. And if there's something else that develops, I'd be happy to just take it. I just want to share DRM datasets. So the idea is you model a source fault and the site, and then it's presented as a Python library. And it's basically a code where you model point sources that represent a large complex fault, and then you have sites, a site where you want to compute your motions. And the big thing here is that we assume a 1D crustal structure, and it's also it assumes a horizontally layered 1D crustal structure. So basically, for these purposes over here, I am basically a flat earther. We assume the Earth is flat, and the crust is a 1D layered cake. So then it's ready to work in parallel. This could work perfectly over there at TAC, but it also works in my local cluster through MPI, so it scales. And you can generate 3D DRM motions for OpenSees directly using the H5DRM data format. Now, in a little example, we're going to analyze a little basin. This is in the ShakerMaker paper. We use ShakerMaker to set up the regional scale problem. We run and we generate an H5DRM dataset. And then the H5DRM dataset is loaded into OpenSees, which has a new load pattern that can read this type of dataset. And you just run your analysis with usual transient simulation options. It's just adding the DRM dataset as a load pattern, and the rest of the model is the same, and you would run it as any other model. So here's a zoom into what it looks like, but I want to talk about the H5DRM dataset and the load pattern, right? It's a new load pattern in OpenSees that can read these datasets. It's based on HDF5, high performance computing data storage format. It's parallel ready, both in the writing of the HDF5 dataset through ShakerMaker, but also if you run it on OpenSees, you can run in OpenSeesMP, SP, whatever you want. It's transparent to that. And because I want these datasets to be shared and not to be tailored to specific models, I've actually programmed automatic node matching of the DRM nodes into the finite element nodes into the load pattern. So the matching is done automatically. You just need to do some geometric setup, and there's some tools for diagnostics and transformation. I'm going to show some of that stuff. So basically here are what some results look like. You have in the top, it's a free field problem with some emotions coming from a simple setup. And then the only thing I do is inside this little basin, I change what the shear wave propagation speed is like. So you get a softer behavior inside there. So if we go into the response of the little center at the top of the surface, if there's no perturbed free field motion, you get that the OpenSees solution matches the ShakerMaker solution. FKDRM used to be the old name of the library, but this is ShakerMaker. So both things match. But then if you introduce the perturbation or the change in the speed of the shear wave velocity inside the basin, you get mismatches. And you also get outgoing waves from the DRM domain. So how do you use ShakerMaker? ShakerMaker basically have to specify the 1D crustal structure and the fault and the place where you want to record and how you want to record. You don't need to do DRM. You can get just single points, and ShakerMaker is going to run nice and fast. So, for example, this is what it looks like to add crust layers. So it's just you initialize a crust model with how many layers you want, and you add crust with their propagation properties. And then here on the other side, you can specify the fault source. In this case, I was doing it at the origin and at a depth of 10 kilometers. And you specify the fault plane and a little source time function. ShakerMaker comes with several source time functions bundled inside. And you assemble those into a fault source, which is a list of sources. So basically, each point source goes into a Python list of fault sources, and then that is what gets computed. And then if you want to specify a station, which is a DRM, a place where you want to do a DRM box, essentially, you use this DRM box command where you specify what the spacing of the nodes needs to be and X and Y and Z, like the number of nodes in each direction. And you create a writer object. And then you need to specify all these things depending on your problem, like the number of this would be a function of your crustal properties and the maximum frequency you want to have. And then you just run ShakerMaker. You create the model by providing the crust, the fault, and the stations, and then you call the run function. And that's the whole script. And then if you have many faults and many stations, this is going to take a long time, but no fear, because we can run this in parallel using MPI. So recent developments in ShakerMaker. ShakerMaker was released in 2020 already, but we run into some problems. Now for the application that I showed you in Santiago, we have 32,000 faults and about 10,000 DRM stations, which results in 320 million calls to the FK core inside ShakerMaker. So that makes it very computationally expensive. So we implemented a solution which is building a Green's function database. And to create that database, you pair up the points and you just figure out which ones are at the same range, distance, and depth pins. There's some approximation there. So you say that nearby points have kind of the same Green's function. That's the idea. And you generate this Green function database, which reduces those 320 million calls into about 60K calls of the FK core, which is manageable with modest computational resources. And then we use this pre-computed database to compute the DRM motions, basically. There's some new problems, is that we need a better way to do the Green's function interpolation for data points that don't fall within a specific range bin, because this introduces some artifacts in the problem. You're already introducing an approximation, and we want to do a high fidelity modeling. So the downside of using the database is that you lower the fidelity of your seismic wave field. And then after talking about ShakerMaker, I want to tell you guys about some aspects of how you need to set up your finite element models to do DRM. So this slide kind of shows over here what a typical DRM model looks like. So you have your feature in the center, and then you have the red nodes represent the interior of the DRM box, and the blue ones represent the exterior of the DRM box. And then, well, this model right here, we'll talk about it later. It's a linear model, but you can have whatever you want inside here. So the soil can be linear, non-linear. In this case, we apply some damping, a little bit of damping. But for the absorbent boundary method that I've been using lately, we're using elements on the exterior boundary with increased damping, 20%. And this is based on a paper I wrote with some colleagues in 2020, I think it's a 2020 paper. And outside here, you can, at all the faces of your domain, you can use fixed boundary conditions on the exterior surfaces. And with this model, you can do anything you like. You can do self-weight first, and then you can do staged. And then when the time comes, you apply the DRM motions. So I want to show you what setting up a model like this in STKO looks like. So over here, if you can still see my screen, I think you can. I have a live STKO instance running and showing this particular model. We can take a look at what's going on inside of this model right here. I think I should be able to at least get rid of some of these parts and to look at what's going on with the DRM box. And so this little plugin that I have over here helps you placing the DRM box wherever you want in the domain, and which is crucial if you're sharing data sets. They're not all going to match. So you need some control over what happens with the DRM motion. So this plugin reflects, and I'm going to show you the OpenSees command for the DRM after this, but this reflects the same option. So it also gives you the possibility to see here what the target motions look like. And these are displacement responses at the center of the DRM domain. That's useful to just at a glance know that you're using the right data set. So I can look at the accelerations here. Now, forget about this part. The motion occurs, the interesting motion occurs the first 40 seconds. That other part over here, which is shown over here, talks a little bit about how ShakerMaker works, because ShakerMaker works in the frequency domain to do some computational improvements or enhancements, right? And things in the frequency domain, you just when you're converting back from the Fourier space back to time, you lose half of the time. So it has to do with the Fourier transformation. But the physical part is this. So those are the accelerations. We're getting about 1g of acceleration in the x direction for this data set. And then with the different options, you can tweak a little some things. So the first thing is you have a coordinate scale factor, so your units don't have to match. So I could have like 1200, and that would expand the DRM box out. I need to make this so that it matches with my mesh, with my model. So you can expand the little box. These are all options available in OpenSees. The distance tolerance refers to the fact that that your mesh might not match, so your finite element might not have a node exactly where the data matches. So you can give DRM here a little tolerance, and then you can move the box around with this top center location. So if I move it, let's say in the y direction, 20 meters, I can move that around, and the box, I don't know if it's visible, but it's a little bit off center. Did it go off center? There it went off center. Okay, there you go. And then let's center it back, because otherwise my academic OCD is not going to be tolerable. But another thing over here is that you can rotate the box with these local transformations. So I could say something like, I don't know. I'm going to mess this up. It's going to look horrible, but bear with me a little bit. Something like this, maybe. So you can rotate the box apply some transformation, and these are just the unit vectors of the x-axis and local y-axis, and the z-axis is computed automatically as a cross product of these two vectors. So it gives you a way to rotate your box around. And because I didn't mention this, but the coordinate system in ShakerMaker is a bit funky. It's with the z coordinate down. So this is why we need to actually use a coordinate transformation over here that considers the fact that the data comes with the z coordinate positive when we're below ground. So that is the STKO plugin we developed with Massimo for input. This is a very neat tool. Like, you can do all these things with open source tools, but this one is really comfortable to have. If you're working with DRM datasets. Another thing here is that you can actually look at how the box distorts over time if you apply some things. It looks kind of funky, but it works, and you can inspect the time series for specific points over here. Okay, and let's go back to the presentation. So that was the STKO plugin demo. And when you use the STKO plugin, what you get is in your TCL file, in your tickle file, you'll get a command, and this command is documented. You can find the documentation link over there, but it's in the GitHub documentation of OpenSees. And you can see what the different command options are, but it basically reflects this widget that plugin widget that we had over here. You can specify the coordinate transformation scale and the distance tolerance. The only one that's not in the GUI is this one over here, which is basically a flag that tells you whether or not to do the coordinate transformation. So if you set that to 0, the transformation is not performed, otherwise it is. When we're doing DRM with STKO, we're just always assuming that we're doing the transformation. So that's how you set up your DRM input. And then next thing that you need to set up is just a reminder to make sure that you're doing wave propagation. So there's no point in doing DRM if you're not going to be thinking about high performance or high fidelity tracking or resolving of the input wave field. So you need your wavelength, your shortest wavelength, so that'll be the shortest shear wave speed over the maximum frequency of interest, to be such, the discretization to be such that you can resolve one wave. And this n here is practically speaking, in the order of 10 to 20 to 10 to 20. And then as your mesh gets smaller, you're also, because of the wave propagation condition requirements, you're also going to need a time step to get smaller as your mesh goes smaller. So your time step needs to be shorter than the shortest discretization size over the fastest propagation speed that you have. So on one side, your discretization is constrained by the minimum propagation speed, whereas on the other side, the time step is constrained by the fastest traveling wave. And the next thing you might be curious is about that absorbent exterior domain. And here, DRM is basically doesn't care what you have outside, it's going to work. It's up to you to set it up however you want. So what I've been using these years is the absorbent exterior domain, which is just using regular continuum finite elements with added additional Rayleigh damping. But Pedro Arduino's and ET's group or work has been on implementing perfectly matched layers into OpenSees, and that work is going along really nicely. We should be having a 3D PML into OpenSees that works, and I think we have it at this point. We just need to start using it. Or you can do a classic approach with Leismer-Kuhlemeyer damping, so basically silent boundaries with dash spots. But that brings in the little trouble of dealing with the boundary conditions. And when Massimo has developed for STKO a nice plugin that uses the silent boundaries. So I haven't used this last approach, but I'm excited to see what it does. I think we can, if we use these two methods, the first and the last together, we can get rid of a little bit or make this absorbent exterior domain a little bit smaller. And so I'm going to tell you a little bit about how to set up an absorbent exterior domain. And this is based off of a paper with my colleagues, Francisco Pinto, who's at Universidad de Chile right now, Cristian Ledesma from Universidad Católica, and my local colleague, Rodrigo Estroza, over here at Universidad de los Andes. And so basically in this work, we, never mind that text over here, but we wanted to know what is the correct setup of an absorbent exterior boundary. So meaning how many elements should I put, how far away should they be, and what levels of damping should we use? And it's for these same buildings. And after you set up a proper absorbent boundary domain, we wanted to see what the damping characteristics of the system were like. So the paper had two objectives. So the first was to take a look at the setup of the exterior system. So here we're seeing the sensitivity of the spectral ratios of two models where the boundary has been set to different distances. And you can see the blue one is the best one over there. And damping was fixed at 20%. So we basically, the takeaway from here is that you can get a good response for these models if you have 10 elements in your absorbent boundary and you set your damping to 20%. That works nicely. And we verified that in this paper by changing the distance to the boundary. And the interesting results that we had for this are that you can get a lot of damping for some buildings. You can get up to 1% critical damping, just attributed only to seismic radiation. This has nothing, no earthquake, nothing else. Damping coming from radiation to energy loss to your medium is 1% attributable to that for this building. And it's also going to depend. B1 and B2 here have different number of basements. So B1 has 2 basements and B2 has 4 basements, and damping depends on how many basements you have. And if you have a taller building with more basements, in this case, B3 has 4 basements and B4 has 7 basements, then you can get also the way the damping works is a bit different because the mechanism that generates the radiation or the waves into the soil domain is different, so you get different dampings. And finally, I want to show you guys some ongoing research results where I've used this whole platform. These are results that I've just gotten this last month. So these are very recent, and I haven't published any of this. I'm going to be showing some of this stuff in the World Conference of Earthquake Engineering in Milan next year. And of course, I intend to publish some of this stuff. So this work, I owe my gratitude to Alberto Hurtado, to your left, who was my student over here at Universidad de los Andes. He's currently an engineer at ASDEA, and he's going to be starting his PhD at Chieti Pescara and Politecnico Barcelona next year under the supervision of Guido Camata, which is going to be exciting. And then to your right is Mr. Omar Oyarce, who's a current master student at UANDES, and he's also hired as an engineer at Andes Lab, which is a new startup, exciting startup over here in Chile. They're doing some fancy artificial intelligence stuff to just get rid of all the civil engineer future. So that's exciting stuff that Omar is doing over there. No, that's I joke, but that's really, they're really doing cool stuff over there at Andes Lab. So I'm really excited to see what Omar is going to be doing the next years. And so here's the setup. Let's go back to Santiago. We need to do this whole process. So we need to go from a fault to cross propagations with ShakerMaker into OpenSees, right? So this is kind of the setup I have for the project. We have the San Ramón fault in the center, and we have several sites. This green site over here is over the hanging wall of the fault, and this is where I am right now. This is in the engineering building at Universidad de los Andes, and then we have several sites distributed throughout Santiago. We have some near field sites, intermediate field sites, and far field sites with respect to the fault. These were just chosen by clicking on the map and getting the coordinates, and that's that. We'll look at other places if we get the time, basically. So the first step here is to generate your fault rupture. And the fault rupture is basically the point sources that you're going to be feeding into ShakerMaker. And this is the result for a magnitude 6.5 earthquake occurring in San Ramón fault. And then again, San Ramón can produce 6.5, 7, 7.2, depending on who you ask. This is highly speculative. But since we're simulating, we can test several scenarios. We can test this case where the rupture starts in the middle, but we can also test where there's a unilateral rupture. So maybe the rupture starts here and propagates towards the north. By the way, here we have slip in the color bar in meters. So 1.75 meters is the yellow of slip. And then the red lines are isochrones. So basically this isochrone every 1 second. So the first second, the earthquake is contained within this. And then the next second, it's expanded out here, and then so on. And then we generate these faults using the UC Santa Barbara method families. This gives us slip geometric parameters such as rake, dip, and everything, and trigger times, which are spatially correlated to resemble empirical evidence as well as simulation results. So they're meant to be physical, and they're meant to mimic the type of variability that you would get when you record sites when you record motions at different sites. So this is a method that has been validated with data in California. Now, application of this method results in about 32,000 subfaults. So hence the problem I ran into, where I needed to use a green functions database. The UCSB methods is going to generate the fault is going to be incorporated into ShakerMaker as a factory during 2024. I'm just finishing. We need to interface it, and but to make it easier to generate a fault, so you just specify what the size of the fault should be and what the magnitude should be, and some other important parameters, physical parameters, and it's going to generate a fault for you that you can then use to run ShakerMaker. So everything I've done here is run in our in-house Esmeralda HPC cluster, which you can see there, and Alberto Hurtado is there for scale. This is a picture I took right before this talk, and it's a little cluster rig consisting of gaming computers. I have a video about this on my YouTube channel. You can check out. But it's a nice way. It's been enough for this project for everything I'm going to be showing here. And of course, with the help of Alberto there, standing to give you guys a sense of scale. Esmeralda is one Alberto in height. So let's go first to check out what's going to happen to me. So let's see what happens at the engineering building at Universidad de los Andes. After you simulate the motions, you get this kind of response. Note that I'm just showing the first, in this case, 30 seconds of motion. This is going to be a fast event. This is what the motions look like. And so then the model that we want to run is the engineering building over here at Universidad de los Andes, which is a new building, which is not yet complete. But the good thing about it is that it's we have all the information about it. And I also have sensors provided by ASDEA hardware, actually, which we're going to be installing more sensors for this building during the summer to do some validation simulations. And we generated this FEM model. We're modeling, okay, let's start with the site. We're using brick elements for the exterior domain, and then 4-node tetrahedrons for the complex internal geometry, because otherwise you're going to go crazy if you want to do if you want to do structured meshing algorithms inside. This is a complex model, right? And then for the shear walls, using ASD shell Q4 elements containing the new ASD concrete material inside. So we're modeling nonlinearity in the shells. And then the slabs are modeled linear for these results, but we're doing some testing whether we can do linear or we need to do some nonlinear in some cases. And the beams and columns are all displacement beam columns with TC3D. I forgot the name of the material that goes inside, but it's a uniaxial material for concrete. Oh, damaged TC3D. It's right there in the screen. And also steel O2 for the steel in the uniaxial elements. But for the shells, we're using plate rebar. We also have a project underway to test different modelings for the shells and the beams for this model. So we're not yet satisfied with where this model is, but it's usable at this point. And okay, so let's get into some fancy videos. Here we have the response with a flat wave approximation using the STKO automation to input the earthquake using silent boundaries. So this is what the building response looks like, and you have in colors displacement, and in the rainbow color you're going to see where the building is getting damaged during the shaking. So this is your level 3 modeling of the building with nonlinear building and linear soil. So I'm not doing nonlinear soil at this stage. This is what the shaking looks like. What's fun about this video is you can see when the building starts breaking, you can see the change in there you go. The change in the vibration frequencies of the building. And then next up, the DRM. Now the DRM, you can see there's a place over here where the input is going to be occurring. So you're going to see that these results look very different from those other ones. The color bars are the same as the previous video. So now you can see the motions are occurring inside the box, and there's nothing outside. Or very little motion outside, and in this case, the box, the shaking of the box induces the motion into the building, and it's fully 3D. So the motions are not correlated. This is not a flat wave, although you can't see it. Displacements are amplified by a factor of 100 to see this video. You can see it, but the motions are different. They're coming from surface waves, but because the velocity of the shear wave velocity over here is 750 meters per second, and the site is rather small, you actually can't see the wave passage unless you just look at the individual time series. So that's the result for the nonlinear building. But let's go look at the engineering result details. So we can see here is the floor spectra. So we're at the 3rd floor. We're not quite at the top. We're at the place where I'm working right now. And you can see in the different lines, the period versus acceleration. These are spectra. And these are, the left one is for the x direction, which is the long along the building, and the y direction is transverse to the building. And you can see in the dotted line is what the fixed base response looks like. And the dashed line is if you are a flat waver, so basically not a flat earther, you're assuming plane waves into your input. And the solid line is DRM response. So you can see for the x direction, the dashed and the solid tend to match up pretty nicely, and they're contained conservatively below the fixed base condition. But interestingly, what happens in the y direction? So the y direction of the building, this building is very torsionally coupled. So basically, we have a stiff core of walls on one side, and then we have this cantilever over here, which makes the mass eccentric. So the cantilever shifts the center of gravity towards x positive, and the shear walls shift the center of stiffness towards x negative. So we have a very exaggerated torsional response. And in this case, we can see that the modeling of the torsional response is sensitive to basically how you're modeling the input field. And we can see that the case of the DRM, we're getting accelerations that go beyond fixed base in this case. And then what tends to happen is that for longer periods, both plane wave and DRM tend to match, but then there's this weird intermediate, but they tend to match, but they exceed the fixed base condition. So anyway, we just have these results, and we're trying to make sense of them. This is what the roof response looks like, and the story is a bit similar with different ratios, I guess. We have infinite number of results that we need to try to make sense. And then you can take a look at drifts. So this is interstory drift. We have plane wave versus DRM. In the x direction, they look kind of similar, but then in the y direction, you can see there's some things going on which are different for both cases. And then we can compare DRM with fixed base, and you can see they don't match. For the case of the fixed base, it's over predicting the drifts. If you consider that the blue DRM line is somehow the truth, which you shouldn't, but that's the best model we have at this point. And the same goes for the y direction. There's a huge mismatch. We can make all these comparisons all day. And we can also, this one's interesting. We can take a look at the damage distribution in the concrete cores. And then you can see that for the fixed base, there's a lot of damage. Whereas if you assume flat wave or DRM, the damage pattern looks essentially the same. So it's not from the damage of the shear walls where the differences are coming. It's more fundamental than that. It has to do with the input characteristics. There might be damage on the columns and beams. We haven't looked at those results yet, so there might be some stuff going on over there too. And then let's take a look. This is going to be the final example I show. What happens if we model tall buildings along Santiago? So right now we're going to move over to that near field station over there at the north or northeast of Santiago, and we're going to put this building over there, and we're going to subject it to motions coming from the San Ramón fault. And this is what these simulations look like. This is a very fun video to watch. I'll let it play for a little while. Some people are very disconcerted by what these simulations look like with that block drifting. You have to remember that inside the DRM box, that's your physical place, and it's moving along because these are realistic simulations. So they do consider that the soil moves, and there's a permanent offset due to the earthquake. There's the earthquake moved soil around 1.7 meters or something, and this place on Earth is moving like 36 centimeters towards some direction. I forget what the orientation is right now, but there's a permanent offset after this. Another thing that is interesting is you can see at the beginning how the motions propagate up into the building. So the base of the building is delayed, or the top of the building is delayed with respect to the base at the beginning. It's nice to watch. It's very relaxing, I think. Obviously, the motions here are amplified. I don't know if by a factor of 50 or maybe 100, I forget. So that's what the response of the building looks like. And then we can do the same exercise as before and take a look at response details. And these response details I just got in this morning. But let's take a look at the response spectrum for the roof. You'd be interested in response spectrum if you're designing secondary elements, so basically non-structural elements or things that are hanging, heavy equipment. You're very interested in this. Whereas if you're designing the structure, you're going to be more interested in drifts, base shear, those kinds of things. So here we can see the different modeling strategies in blue, DRM, in dashed orange, fixed base, and in green, it's the absorbing boundaries. And you can see there's a place where DRM is winning in terms of response spectral ordinates for the floor motion. In terms of drift, here in this chart, I have along the x-axis interstory drift, and the vertical lines are limitations for interstory drift due to the Chilean code. And then the lines represent the maximum center and maximum corner drifts in the X direction for blue and orange, and in the Y direction for green and red dashed. And you can see this. So this is for the fixed space condition. And if I now move into the absorbing boundary condition, you can see here I'm switching between fixed base, absorbing base. So you can see it's beneficial. It looks beneficial. And then if you go into DRM, forget about what's going on down here. We need to come up with an explanation for this. Maybe it's a post-processing error. But what you can see is the shape of the drift is different, and you can also see that we're exceeding what the code is providing for this one station, and we can move to another station and do the same kind of plots. And here the plots look similar. We're interestingly enough, we're closer to the fault, but we are within limits of the. So there's some rupture propagation characteristics that enhance the results over there. And then if we move to a station over there, up there in the north center or intermediate field, you can see that in this case, fixed base, absorbing boundary goes down, and then DRM actually goes up. So in this case, DRM the results are a bit worse, but still be within the limits of the code. So these are the results I wanted to show you up to now. And for now, thank you for your attention. And I'd love to hear your questions if you have and your comments. I guess there's one question in the chat.
Yeah, there was one there. I'm not sure which slide that was. You are attendees, you are able to unmute and talk actually. So if you'd like to ask.
Okay, but Sukumar was asking, do I mean numerical damping coming due to numerical reasons in the last slide? Sorry, I didn't catch which one this, but I was probably talking about the damping of the DRM layer in that case. If it's not that, maybe you can tell me if that's what you meant. But it's not numerical damping. It's well,
I was talking.
It's an additional physical damping that you're using to model the seismic radiation in that case.
Okay, I was asking about those building B1, B2, B3, B4. Do you remember now?
Okay.
Can you hear
yes.
me? Can you hear me?
Yes, I can hear you. I can hear you.
Yeah, I was talking about those buildings, B1 to B4. There you said damping has increased. I didn't actually get it. So that's why
Here. Let me put these slides on. These ones, right?
Yeah.
This is radiation
You're talking
damping.
about
So
this critical damping thing.
No, in this case, this is free vibration of these buildings. These buildings are hit at the top with a impulse, and then you see what the decay of the building is.
You mean these are model dampings?
Sorry?
Are these model dampings at different modes or?
Model dampings, yes, at different modes.
Okay,
Correct.
okay. Now I got it.
And
Thank
it's
you.
purely, it's because it's a modeling thing, so it's purely due to the seismic radiation. So the building is shaking. There's no damping for the building, no damping for the soil nearby, only damping at the exterior boundary. So we're only getting energy out of the system from the radiation, allegedly.
Okay.
So if you have that setup, you can attribute up to 1% damping, in this case over here, to mode 1. Yeah.
Okay, thank you.
Any other questions? Feel free to unmute or put something in chat is fine.
Can I ask something about OpenSees SP?
Yes. I can
Yeah,
answer.
I'd like to know.
Massimo, so.
Yeah, OpenSees SP. I suppose it works on the basis of shared memory, same CPU, but many
No.
cores. Am I right?
It
It is MPI or OpenMP?
It's MPI.
Okay.
Both
So
SP and MP
write
are both MPI. So you have a distributed memory, and everything occurs with MPI.
Okay, in that case, I need to write the script in a different manner.
So in the case of
Or the same script works?
SP,
OpenSees script.
it's pretty much the same script. You would probably need to change the analysis options to deal with the parallel part. And then OpenSees will take care of the model partitioning for you, and that's very comfortable. But it's limited in the sense that if you're going to very large models, you need to first load the whole model in your rank 0 processor, and then you need a lot of memory for that, and then it gets distributed. And it also, there's some limitations because that distribution phase requires that all the elements that you're using and all the materials that you're using and everything basically implements some specific member functions to handle the transfer. So if you're using some component that has not that part implemented, it's not going to work. So whereas in OpenSeesMP, you would write scripts for each partition, or one script, but it has if conditions depending on what partition you're dealing with. And it's more scalable also. So it's a good thing. Those things
I don't find much
STKO.
of documentations on this. Can you point me to some good documentation or some tutorial kind of thing for this?
About which one?
OpenSeesMP, say?
Out of the top of my head, I don't know. I don't know if Massimo maybe knows if there's it should be the OpenSees website, but I don't know.
There are few examples on the OpenSees website. So if you go to the official OpenSees website, then there is the parallel section. There are some examples, not so many because writing OpenSeesMP files manually is complicated because you have to deal with partitioning the model. You have to understand how the partition works. So when a node belongs to only one processor or when it goes to multiple processors, how you have to handle boundary conditions. So it's not so easy. That's why we decided to implement it into STKO. So the user just has to partition the model, and then STKO will take care of modeling, of creating the TCL files. But there is a very basic example, like a 3-truss kind of model that explains you how to split it into 2 subprocessors, and it's on the official OpenSees website.
Okay, thank you so much.
Welcome.
I will add that we have some recently updated documentation on OpenSees that is on the DesignSafe platform in our user guides, but it is generally applicable to not just DesignSafe, to not just using OpenSees on DesignSafe. So there is some good information about OpenSees SP and MP there as well. And Dr. Sylvia Mazzoni, who's a longtime developer and user, earthquake engineer of OpenSees, worked with us to develop this. And she did a webinar in early November walking through some those examples and talking about the different types of OpenSees and how to use them and how to use them in design safe in particular. But again, the information is broadly applicable to using it on your laptop, using it on other HPC systems, any other resource. So,
okay, thank you. Thank you so much for that information.
okay. Any other questions? Jose, thanks. Thanks again, and thanks to STKO for the STKO folks at SDS for organizing things and coordinating with Design Safe on these. STKO is available through Design Safe as well. We are updating to the most recent version. Massimo, I think we're still in process on that. Is that correct?
Yeah, it's still a process. I send it to your colleagues, and I'm waiting for their feedback. But yeah,
Yep.
we are working on it.
Yeah, so we will have the updated, most up-to-date version
most updated.
available through Design Safe soon. And as I mentioned earlier at the beginning of the webinar, most anyone in the world is available to access Design Safe. So you're welcome to do some work through our user portal. All right. Well, thanks everyone again.
Thank you, Tim. Thank you very much for organizing this. And Guido.
Very good. Thank you, Guido.
Thank you, Guido. See you around.
And thank you, Jose. Thank you very much. Very good presentation. I loved it.
Thanks. Thanks. You're very kind.
Thank you, everyone.